So, welcome to our lecture, Energy Management and Demand Side Management. In previous lecture, we were discussing about the basic concept of energy management. And for the energy management, it is very much necessary to understand the electric tariff. So, till this one, we have come to know the different type of tariff is there, and the tariff, why this tariff is important, because the tariff have a very good uh, tool for the energy management. So it tells how to conserve the energy, and in which time the energy consumption, or say we can say that in which time the energy rate is different or say higher one, and in which time the energy rate is a smaller one for the 24 hours. Okay. So in the electric tariff we have discussed that the simple rate tariff, block rate tariff, commercial rate tariff, and industrial rate tariffs are there. So in the last topic which we are discussing about the HT tariff. So HT tariff consists of maximum demand charges are there. Maximum demand charges are there, and say just a minute, someone. Okay. So there is some pause are there. Okay, now we will start. Okay, so maximum demand charges in kVA, energy charges, that is the actual energy consumed by the consumer. Nowadays it is a kVAh billing is there. So your maximum demand charges and power factor penalty comes into the kVA. Billing charges still it is there. It is depend upon the number of unit consumed by the consumer. Power factor penalty, if the power factor decreases zero point 0.9, 0.85, then then there is a penalty. And if the power factor increases from 0.95 to 1, then there is a incentive. Fuel cost adjustment charges, electricity duty, it is a depend upon the number of unit consumed by the consumer, and total amount, it is a 21% for the commercial and 16% for the residential type of tariffs are there. Time of day tariff, it is used for the more than 20 kilowatt connected load, either it is in the LT side, and no doubt it is definitely there for the HT type of consumer. And penalty for the excess demand charge, if the your maximum demand occur more than the contract demand, then you have to pay the maximum demand charges, penalty is there. So this is the example of HT commercial 2 type tariff. There is a different type of tariffs are there. In the HT, it is a commercial, industrial, and then government sectors. For non-government sectors are there. So demand charges presently it is 411 per kVA. Energy charges, it is a 9.41 per kWh. Billing charges is 0.57 per kWh. Nowadays it is depend upon the kVAh billing, which we see one by one. Electricity duty for the commercial, it is a 21%. Electricity duty for the residential, it is a uh, this one for it is at 16%. Cell tax, it is a 8 paise per kWh. Then power factor penalty is there, and power factor incentive. Power factor penalty, it is a 10% to the 0% when the power factor is zero point 0.9, and 0% penalty is there. But when the power factor goes toward the lagging or leading a smaller value, you have to pay penalty. Similarly, incentive at 0.95 there is no incentive, but as soon as the power factor increases 0.95 and above up to the unity, you will get the some power factor incentives are there. Okay. Okay, now this is the demand charges. This is the time zone is the TOD is there. Something is wrong over there. So now it is a zone A, uh, is 10 p.m. to 6 p.m. Then there is a say minus 1.0 rupees, and zone B, it is a there is a no additional and subtraction in the basic charges. Zone C, that is 9 a.m. to 12 uh, noon, so plus 80 paisa get added in the basic rate. And zone D, this is 6 p.m. to 10 p.m., this is the peak demand, and during that peak demand you have to pay the more electricity charges, that is additional 1 rupees 10 paisa in the basic rate. So this is points which we have considered. Now power factor incentive is there, and power factor incentive, it is a 0 at 0.95, and as 0.96 the power factor incentive is 0.1% of the total charges. If your electricity bill is 1 lakh, then it is a 0.5% you will get a benefit of the power factor improvement. And if you are maintaining the power factor is 1, that is a 3.5% you will get the benefit from this one. Similarly, the power factor penalties are there, which already we have discussed. Just I have taken the some highlights of this one. Now, this is the point which we have to consider very carefully, is a power factor computation. Earlier, what we are doing, we are measuring the power factor, that is the average power factor, it is equal to the total kWh divided by total kVAh. So if you draw the reactive power or active power triangle, that is the power triangle for the load. So active power consumption is the kWh divided by the apparent power, total apparent power, and the total apparent power, that is the kVAh, is calculated by this formula. It is the sum of kWh square plus sum of R kVAh. Only it is the reactive lagging is going to add it. Here we are not considering what is the capacitors, either it is a fixed capacitor is connected in the system. For example, in the daytime your factory is running, so you are maintaining the power factor by connecting some fixed capacitor. But in the night time, say it is a only one or two shift working is there, so in night time what we are doing, we are shut down our machineries, whereas your capacitor will remain connected in the system. So when the fixed capacitors are remain connected in the system, what it do? It will increase the power factor and goes toward the leading. So either it is a zero point 0.8 or zero point 0.5, say zero point 0.6 or zero point 0.7, 0.85 leading power factor. So we know that from our all calculation, the power factor may be leading or may be lagging, it will draw more current. And whereas the current will be minimum only when the power factor will be unity. At the same time, when the lagging kVAR is smaller, that is the deficit of the lagging kVAR, the voltage get decreases. So voltage profile get decreases. Whereas if there is a surplus of the reactive power, that is the capacity one, then the voltage, terminal voltage get increases. So if you are not maintaining the power factor at unity, the voltage may increase or may decrease because of the lagging kVAR or leading kVAR. So in new method of the calculation, it is found that in many of the industries, fixed capacitors are connected, and during night time or during light load, especially for the night time, the fixed capacitors are remain connected in the system, and they are people are forget to go disconnect it after disconnecting the total entire production load. So what happened? The leading kVAR flow over the grid, and that leading kVAR play, it will increase somewhere voltage, or it will make the complication in the power system stability and the security. So the new method of calculations are that power factor, the kWh is as it is, whereas kVAh is going to calculate by, the first part is as it is, the summation of active number of active energy consumed by the consumer plus summation of reactive kVH and capacitive kVH, that is lagging kVAh and leading kVH, their addition and bracket square. So it is quite clear that now it become very difficult to maintain the power factor is equal to unity. Here only RKVAH, that is a lagging KVR, is going to calculate, whereas whatever the value of capacitive reactor, or capacitive reactive power is there, it is considered as 0. Then the power factor is become a unity. It's a very simple to maintain the power factor, and they are calculating the power factor is 1. But here the average power factor become very difficult to maintain the unity value by this formula, where the kVh is equal to summation of active power square plus summation of lagging kVh and leading kVah bracket square. So under this new method of calculation, the power average power factor maintenance become a challenge to the consumer. So now it is very much necessary to use the APFC, that is the automatic power factor controller. So automatic power factor controller, in this automatic factor controller, there is no fixed capacitors are there, or it is advised or it is given some suggestions to the all type of consumer in Maharashtra, just disconnect your fixed capacitor and go to the APFC, automatic power factor controlling. So when there is a automatic power factor controlling, as soon as your load decreases, the number of capacitor get decreases. So for example, in our college one, we have a 100 kVr capacitive bank is there, and it is divided into the number of step, that is 20 kVA plus 20 kVA, this is second step, then 15 15, then it is a 5 10 3 2. So in this way, you can arrange, or you can arrange the number of say steps, and it will give the smooth variation in the power factor. No doubt, if you are increasing the large number of small capacitor, you can give the fine adjustment in the power factor, but there is a limitation. So for that one, we have divided in the capacitor is 3 kVA and 2 kVA, so it become a 5 kVA. So if you need a 12 kVA, so it start one 10 kVA unit and two and one 2 kVA unit. If you are keeping 5 kVA and 5 kVA capacitors are there, then you cannot find the value of 13 and value of 12 kVAr. So the number of steps to be properly designed, so that it will gives the smooth variation in the power factor maintenance. So whenever you find the fixed capacitors are there, it is necessary to replace that fixed capacitor by the APFC, automatic power factor controllers are there. Only very small amount of fixed capacitor may be connected for the compensation of the transformer, and this should be connected before the APFC. So it will take care the reactive power drawn by the capacitors, sorry, leading lagging kVr supplied drawn by the transformer only, whereas the load change is going to reflect in the switching on and switching off the capacitors. So this formula is we have to remember. Now this is the case study that is based on the kVAh billings are there. So in April, this is the because the college has a one solar plant also, so this is the solar generations are there. It is the energy taken from the MSDCL, so it is a power from MSDCL. It is the total consumption, whatever the power generated inside the generating plant, our that is a solar plant, plus power taken from MSDCL. So this is the total consumption in the campus. Maximum demand occur in the different month. Power factor that is going to maintain by the APFC and fixed capacitor. The fixed capacitor is only 4 kVr, which is used for the compensation of transformer. Electricity duty, because it is considered as a commercial connections are is there, and therefore we have to pay 21% electricity duty, total electric bill, and power factor incentive. So the minus sign indicate there is a incentive, and plus sign means it is a positive value, then it is a penalty is there. So it is found that this is the maximum demand occurs with a seasonal variation in the temperature also. So in April, May, the maximum demand occur is more, and whereas in the January and December, the maximum demand is a smaller one. Okay, so here it will indicate the maximum demand. Maximum demand is nothing but the simultaneous loads are connected to the system, or simultaneous load are in operation in any particular for the any one type of consumer is there. So power factor, if you look at this power factor, you will find that the power factor is very much nearer to the unity. It is a 0.99, 0.98, 0.97, and so on. So there is no one. It is the last one also. The 0.993 is there. Okay, so you find that the power factor is almost one, and therefore we are getting the incentive in every month. So up to the January, we are getting up to the say December, the power factor is incentive is very high. The reason is that your electric bill and the rate of power factor incentive also with a very high. You will find that this is a 30,000 incentive is there. At the same time, your electric bill will be very high. And in case of the December and January, the electricity bill is smaller, so your incentive will be smaller because it is the 5%, sorry, 3.5% maximum of the total electric bill. So therefore it is very much necessary to maintain the power factor, and this has to be done with the help of only APFC in the new scenario of calculation of average power factor. Earlier it is okay, we can use the power factor controlling by the fixed capacitors. So now what is the kVAH billing? So this is the new which has been introduced in Maharashtra since April 2020, in the same year, same financial year. Instead of calculating the kWh, they are using the kVAH. So here the electric bill become simple. So understanding is very simple. The power factor incentive and power factor penalty get added in the a single unit, and also it is quite clear that even though your power factor is leading, then the kVAH will be very high. Okay, so to maintain that KVAH, KVAH billing, you have to maintain anyhow the power factor should be a unity. Otherwise, either it is a leading side or either it is a lagging side, your KVAH will be higher than the kWh. So our objective is to maintain minimum difference between kWh and kVAH. This is the this one. So it is a vector sum of two component is called as apparent energy, and it is measured in term of kVH. In kVH based billing, the fixed and demand charges are lived over the apparent power, that is a kVA. So your whatever the maximum demand charges is depend upon the kVA, which is earlier the same, and energy charges is based on kVAH instead of active energy consumed by the consumer. In future, energy charges will be live based on the apparent energy, that is the kVAH consumption, which is eliminate the requirement of charges active and reactive energy separately. So if you look at to the electric bill, it is quite complicated. Now the electric bill becomes simple because there is only one charges is there, that is based on the kVAH. So kVH billing, what is the change over there? The maximum demand charges is remain as it is. It is depend upon the kVA, kVA, whereas the energy charges has been changed from the kilovolt ampere hours, that is the kVAH. Earlier it is a kWh. Okay. Rest of the system as it is. So whatever the change in color, it is has been changed in the electric bill. Maximum demand charges as it is. Energy charges, whatever the energy charges is there, it is not based on the kWh, it is a kVAH, whereas the billing charges is as it is based on the kVAH, and power factor penalty and power factor incentive is immersed in the kVAH. So there is no need to calculate a separate power factor um, incentive and penalty, whereas the fuel adjustment charges, time of day tariff, that is TOD charges, electricity duty charges will remain as it is. Rest of the system will remain as it is. So now the case study for the kVAH billing is there. So now look at to this figure. This is the energy generated from the solar. So solar energy, energy taken from the MSDCL, It is from the April, and in April, because of the lockdown, the consumption is very small. We have taken only 3,800 unit from the MSDCL, and it is the bank, the excess energy of the generation is a bank, that is on the grid side. Total consumption is there, and we found that the power factor is 0.988. So what is the kVh? Here, see here, this is the active energy. This dark green color is the active energy. 3802 is the active energy consumed by the college. Whereas kVh billing, it is higher, 3848. Why it is higher? Because it is a 0.988 lagging. Power factor is 0.988. If the power factor is 1, then whatever the energy, actual energy consumed by the consumer, and kVAH billing amount, billing kVAH is same. Now see here, here the power factor has been decreased by zero point 0.5. So see, there is a drastic change. The active energy consumed by the consumer is 5030, whereas the billing kVH is double, nearly double, it is 9246. Whatever the charges is based on kVAH. So you have to maintain the power factor. If you are not maintaining the power factor, the bill will be very high. See, again, we have maintained the power factor. It is because of the lockdown. Nobody is there in the substation, and some of the fixed capacitors are remain connected, which I have told what is the difficulty. And here the we have improved the power factor 0.823. So still the difference in kWh and kVAH is there. So 300, 3859 and 4689. So again you have to pay the more charges because you have not maintained the power factor. Now here the power factor is maintained 0.996, so it is very much close to the unity. So you will find that there is no much more difference, hardly 6 to 7 units difference are there in the actual active energy consumed by the consumer and apparent energy or kVAH energy consumed by the consumer. So this is the way, if you have a improved power factor, we can maintain the kVAH, a smaller value of maximum demand. The maximum demand will be the smaller one. So power factor maintenance is a first lesson to do the energy management. So it has a numerous advantage, technical advantage as well as the economical advantage. Technical advantage is that if you are maintaining the power factor, the current drawn by transformer, current drawn by load will be smaller. Definitely, when the current is smaller, the switch gear, whatever the MCCB, MCB, and circuit breakers are required, will be of a smaller capacity. And hence, if the current is smaller, there is no problem of overheating and maintenance also. So if you are maintaining the power factor, the maintenance toward the switch gear will be smaller. So these are the technical advantage to maintain the power factor. Whereas the economical advantage, if you are maintaining the power factor is small, your maximum demand will be smaller, which will is going to measured on the kVA. Your kVAH will be smaller, so your ultimately electric bill will be smaller. So it has a key role in the technical as well as the economical advantage in the energy management. So this is the power factor, influence of power factor over the energy management. Now here see, you can see the power factor analysis over there. So this is again, it is a kilowatt, kVR lag, kVR lead, and total kVAH. These are the readings, continuous reading of energy meter, and whereas this is the difference of previous value and current value. So this is the actual energy consumed by the consumer, actual kVAR lagging, kVAR leading, and difference of these two will be the kVAH and the power factor. So see here, the leading kVAR, it is 119, whereas lagging kVR it is 497. So the lagging kVR is more, so power factor will be lagging. So it is 0.998 lagging is there. Now, in everywhere we find that the leading kVR will be smaller as compared to the lagging kVR. So the power factor is lagging. Only in this area, in this month, we found that the leading kVR is higher one, and lagging kVR will be smaller. Is smaller, so the power factor is leading. So in the power factor analysis itself, it indicate that uh, we are maintaining the power factor very carefully, and it is close to the unity. And when the power factor is close to the unity, definitely the losses in the system, distribution losses, uh, then overheating problems, failure of connections because of the overheating, failure of MCCBs and NCBs, circuit breaker will be smaller, and again it will give the remarkable uh, reduction in electric bill. So power factor maintenance is very important. Now, electricity load management and maximum demand control. So why it is important? Because in any type of electric bill, especially for the industrial or the consumer who consumes more than 20 kilowatt, there is a two major part of electric bill. One is the constant charges, one is the demand charges, and second is the energy charges. Energy charges is nothing but the actual energy consumed by the consumer, whereas the maximum demand is going to occur in the factory or in the premises, depend upon the number of say loads simultaneously working in the same period. So if you are able to reduce the maximum demand, definitely we are able to reduce our electric bill. But what is the way to reduce our maximum demand? The maximum demand can be reduces by one way or two way. One, by maintaining the power factor, which we have already discussed. If we maintain the power factor, what is the power factor? What is the maximum demand in kVA? Maximum demand in kVA is equal to kilowatt divided by power factor. If your power factor is 1, so your maximum demand will be smaller. If your power factor is say zero point 0.8 and kilowatt is 100, so it is become a 120. So by improving the power factor, we are able to reduce our maximum demand. Second, this is the first method. Second method, if you just say study the essential feeders and non-essential loads, means essential feeders, non-essential feeder. uh, if you run your non-essential feeders or non-essential load in the night time, definitely we are able to reduce our maximum demand. For example, in any factory, there is a effluent treatment plant and water pumping system. So it is not necessary to run your effluent plant in the peak hours, that is 6 p.m. to 10 p.m., or say in the daytime. You can shift into the night time. The night time we will get the benefit of electric rate. The electric rate is get decreases by 1 rupees 10 paisa or 1 rupees 50 paisa. And what is the time? The time is 10 p.m. to 6 a.m., night 10 p.m. to morning 6. So if you run the pumping system, if you run your refrigeration plant, then definitely it can be able to reduce the this one. We can reduce our maximum demand. So this is the way by which we can able to reduce our maximum demand. So as the demand charges constitute the considerable portion of electricity bill, from user angle to there is a need for integrated load management to the effectively control and maximum demand. So this is the maximum demand. So in the next time we will see the demand control in detail.